So welcome to the final session of the day. So our first speaker is going to talk about machine learning techniques, and it's Javier Mauricio Duarte. So let me welcome the first speaker, and the floor is yours.
Okay, thank you. Okay, thank you. So today I'll be speaking on behalf of the ELISE, ATLAS, CMS, and LHCb collaborations, and I'll be talking about novel machine learning techniques. So just shown here is a little graphic of all the different subtopics in machine learning, and I made this a little while ago, and I swear as soon as I made it, it immediately became out of date because the techniques are constantly evolving and new techniques are constantly being developed and applied to these experiments. But before I get to these new techniques, I just want to actually emphasize that there's a long history of particle physics applying machine learning techniques, actually going back to the 1980s. So initially, the neural networks were even applied. There was the idea to apply them to charged particle tracking, which is actually kind of astounding because it's eerily similar to projects that are ongoing right now for the high luminosity LHC, like ATLAS project, GNN for ITK, and other similar projects in CMS and TrackML public data sets. And from there, we also applied machine learning techniques that were crucial for the Higgs boson discovery in 2012, crucial to get us to the significance needed for the actual, to claim observation. So these are, so there's this long history that we have with particle physics and machine learning. So suffice it to say that machine learning has changed the way we do physics searches and measurements. And I think that it's twofold. There's two things. One is that it is an essential and versatile tool that can improve existing approaches, but that it also enables fundamentally new approaches. And so I'll try to describe some of those fundamentally new things that are happening. And of course, there's way too many things going on for me to cover in a 20-minute talk. But I'll try to focus in on a few areas. So one is improved classification, calibration, and uncertainties. Another is faster simulation with machine learning. And a third is unfolding. And finally, I'll talk about how we're using machine learning for anomaly detection. So first, improved classification. So great strides have been made to leverage the rich low-level information that's available in our data with more advanced machine learning techniques. So especially for the task of jet classification. So in the early days, we might take jets and try to summarize them in high-level features that are kind of expert engineered, with theory inputs, things like the jet mass, number of particles, maybe like tau-2-1 jet substructure variables, and so on, and then apply like machine learning techniques to this representation of the jet. Later on, it was realized we can actually leverage techniques that are designed for natural language processing and computer vision. So take basically sequences of particles as jets, or even take their images directly from the calorimeter and apply these machine learning techniques to those with excellent results, actually. More recently, there's been sort of more bespoke representations, things like graphs or point clouds, where we actually are able to represent the particles in a more natural way that embeds the symmetries that are present in our data. And so one example of the improvements that come from treating our data in this way is shown here. So both in CMS, using the particle net and particle transformer models that I'll talk a little bit more about later, and in ATLAS, the so-called GN1 and GN2 methods. And so shown here is actually just recently, so basically improving the machine learning architecture from this DL1 on the left to this GN2 on the right. Essentially how this improving the architecture and representation of the data has improved the classification performance. And shown here is for the task of B-jet tagging. So both the C-jet rejection on the left and the light jet rejection on the right have improved by basically a factor of 4 in recent years, just from these improvements. To show the sort of similar impact in CMS, this result was shown earlier today, so I won't focus on it too much, but I just want to emphasize real quick the difference that machine learning makes. I'm showing here an earlier result from 2016 from a partial data set, and it's a search for boosted Z prime decaying to 2 quarks, reconstructed as a large radius jet. So the 2 quarks are merged in a single jet. And you can see here, basically, what I want you to focus on is basically the W mass peak. So that's kind of telling you how well we can pick out the W mass peak from the rest of the hadronic background. So you can see that there's somewhat of a peak you can observe over the following spectrum. And this is using traditional jet substructure methods. So with machine learning, this is using this particle net graph neural network discriminant. We can see a much more prominent peak is present now in the data. This is using the full run-2 data set. And with that, we are able to set stringent limits on the coupling of this hypothetical Z prime boson to quarks. So another way that we are, so as I said earlier, we're using this particle net model to basically identify Higgs bosons decaying to 2 quarks versus QCD large radius jets. This is actually done using a highly granular multi-classifier, so you can see all the different classes that are being used here. And this is also done in a mass agnostic way, so irrespective of the mass of the decaying resonance. We've actually extended this approach and so gone further to a larger array of final states, including Higgs bosons decaying to 2 vector bosons, both in the all-hadronic state, so where you have maybe 3 quarks or 4 quarks in the jet, and as well as the semi-leptonic mode. So you can see those in the top right. So basically extending to a variety of additional final states. And the way this is done is using this global particle transformer algorithm that uses this learned attention mechanism and pairwise features to basically give more weight to certain particles and disregard others in order to identify the origin of these different jets. And one challenge that we have with a lot of these algorithms is we want to be able to calibrate them, but we don't necessarily have a standard model analog that we can isolate in order to measure scale factors for that particular signal. So there's been this new technique developed that uses the so-called Lund jet plane for calibration. I don't have time to go into the details on it, but to summarize it, we can effectively measure scale factors per quark subjet. So for example, we can isolate a sample of hadronically decaying Ws, and then measure scale factors basically per quark subjet, and then apply these scale factors to more exotic signals like Higgs bosons decaying to vector bosons to 4 quarks in a single jet. So with these tools in hand and with this calibration, we can actually perform a new search for boosted di-Higgs decaying to 2b quarks and 2 vector bosons in the all-hadronic final state. So in this case, you end up with 2 merged large radius jets sort of recoiling against each other. And shown on the left there is the mass distribution actually for the 2 bottom quark jet. And there you can see that what the new sort of signal would look like. This is in the vector boson fusion channel. So showing like what sort of BSM new physics might look like in this very, very enhanced signal. Unfortunately, we didn't see any of this signal. So what we can do is proceed to set limits. And actually, it provides the second best constraint on this HHVV coupling, this quartic coupling called kappa 2v from the CMS experiment. So just behind the 4 bottom quark result as well. But we don't only have to apply this particle transformer to large radius jets. We can actually also apply it to small radius jets for B tagging, for example. And there's a new unified approach from CMS that uses the same architecture to not only tag the heavy flavor, but also tag hadronic taus, regress the jet energy, and also estimate the jet energy resolution. So the result shown here is just the jet response. And you can see the new approach, this unified particle transformer in blue, versus the previous result, which actually uses this particle net architecture shown in red. And there you can sort of see the better jet response, the closer to 1 jet response over a wide range of PT. One thing that this model is is concerned with is the idea of robustness. So it uses this rectified normed gradient method, or RNGM adversarial training, to improve the robustness. And the way this is done is basically during training, the inputs are randomly perturbed in a specific way in order to sort of resemble mismodeled inputs. And then you're forcing the model to be able to adapt to these perturbed inputs. There's a lot of results shown on the ROC curve on the right, which is the misidentification rate versus the B-jet efficiency on the x-axis. But I want you to focus in on is that there's 2 curves, the orange curve and the purple curve. And what you see is they basically have the same performance on the nominal sample. So basically, whether you train with this new approach or the traditional approach, you end up with the same performance on unperturbed samples. But then when you perturb the sample, you actually get better performance with this new training method. So essentially, you have a model that's more robust to possible different ways that the inputs can be mismodeled in simulation. And calibration's in progress for the 2022 and 2023 data. One other way we can apply, or one other way that transformers are being applied is actually for particle ID in the ELISE experiment. So this can result in higher purity and efficiency than standard methods. So just shown here is the result for proton particle ID. And again, it's using this transformer method. And one of the things that they're working on is actually trying to use domain adversarial neural networks to mitigate data simulation differences. And this basically trains a second neural network to try to distinguish between data and simulation and penalize the network for any differences it picks up on. So finally, talking a little bit more about analysis-specific training. So the way that we normally train our classifiers for any specific analysis looks something like this. It's basically primarily concerned with signal versus background discrimination without considering the effects of systematics or anything else that can affect our ultimate figure of merit, which is usually the uncertainty on some physics parameter of interest, for example, like a signal strength for a given signal. So the workflow looks something like this. You have your initial training data set of simulation with some labels. You train it to distinguish signal versus background with this sort of standard loss, categorical cross entropy. This gives you like an output discriminant. Maybe you bin that discriminant, and then you can fit, for signal versus background in this discriminant after binning it in a histogram. So then you extract, your signal strength and its uncertainty. So one thing we can do is basically implement this entire analysis chain that I just described in a differentiable way. And what this does is this allows us to optimize directly for the uncertainty, so the figure of merit, for example, like the significance, in the neural network training. So we need this to be differentiable because we want to optimize a neural network with gradient descent. So we need to be able to compute gradients. So the key to this is being able to choose gradients for the histogram operation, because this is obviously a very discontinuous operation where you're essentially have a piecewise or a piecewise step function. And so I won't go into the details of how this is done, but once you have this done, what you can do, and shown here, is basically the difference between the standard training on the left and this systematic aware training on the right. While the standard training basically makes it so the signal peaks more to the right, this new systematic aware training actually tries to concentrate signal in bins with smaller background uncertainty. So it doesn't necessarily give you the most signal at high values of the discriminant, but instead it makes sure that there's lower background when you need it, lower background when you care about it. And with this approach, actually, the total uncertainty on this signal strength, this is in a Higgs to tau-tau analysis and simulation, the total uncertainty improves by about 25%. So just showing you the shrinking of this -2 delta log likelihood curve for the new training shown in red and the previous training. OK, so switching gears a bit, I'm going to talk about how we can use machine learning to to basically shortcut or do faster simulation. So first, why do we need to do this? The critical thing is that the high luminosity LHC is coming, and simulation is a key driver of the increased CPU needs for the high luminosity LHC. So machine learning can be used to basically shortcut our simulation needs, especially when we need, for example, additional samples for evaluating systematic uncertainties, or, for example, when we want to get new simulation because new higher order corrections have been computed. So first, I'll talk about how we can actually try to replace the slow Geant4-based simulation of Atlas, for example, for an Atlas calorimeter, with fast generative machine learning. So in this method, a generative adversarial network is trained. And the way this works is basically you train this generator, which is a model that takes as input noise and then tries to output realistic showers, and basically tries to fool a critic neural network. And that critic neural network is basically trained to, or is trying to discriminate real or showers from Geant4 from the showers that are produced by your machine learning model. So you play these two networks against each other during training and eventually converge to a model that can basically produce realistic showers that look similar to Geant4. So GANs trained in this way can parameterize the detector response to photons, electrons, and pions. And so shown here is basically the shower energy distributions from Geant4 as well as from these machine learning methods. And what you can see is there's good agreement between these machine learning methods and Geant4 for showers for a wide range of energies. So on the left is a shower of 4 GeV. On the right, there's a shower of 260 GeV. So you can see there's good agreement across this range. And this method is much faster, like orders of magnitude faster than our standard Geant4 chain. OK, so another method we can use to basically shortcut our simulation needs is neural network reweighting. So the way this works is if we want to reweight a sample, let's say it's generated from P1 of X, a PDF, to a sample that's derived from P0 of x, we basically need a weight function that's the ratio of these two PDFs. So what we can use is this likelihood ratio trick, where we train a neural network classifier, f of x, to distinguish these two samples. And then basically f of x divided by 1 minus f of x is exactly this weighting function that we need. So in CMS, there are use cases for this reweighting in top quark physics. So one is reweighting the Monte Carlo for the evaluation of systematic uncertainties, and another is the reweighting of Monte Carlo to higher order theory predictions, for example, from NLO to NNLO. So the way this works is we take the parton level information and input it into this particle flow network. So in this case, the information is the 4-vector, the PT eta phi mass, and PID of the top quark, anti-top quark, and TT-bar system of the showered events. And from this, we basically learn this weighting function. And here what's shown are the results. So for the original distribution is the NLO one in green. The target distribution is the NNLO one in black. And then the reweighted distribution is shown in red. And you can see that the method closes within 2% of the target NNLO distribution. So what this allows us to do is basically skip the more expensive simulation steps when we have a new higher order correction, because we can essentially reweight lower order Monte Carlo to that. OK, so next I'll talk about how machine learning can be used to unfold our detector response from our results. So in this analysis, Omnifold is used to unfold 24 Z plus jets kinematic observables at particle level in Atlas. So the way it works is there's like this iterative process. Detector level Monte Carlo is corrected by a reweighting function to match data. After this particle level Monte Carlo is actually corrected by another reweighting function that's a function of the particle level information. And it's trained to match basically the data corrected Monte Carlo. This process is repeated 4 more times, basically just to get good convergence of these reweighting functions. And the final measurement is not actually just like the bin distributions of the observables. Instead, the final measurement is actually the reweighted Monte Carlo events, which are reweighted to match what we see in data. And so shown here is basically all 24 one-dimensional observables after this unfolding is done. I don't expect you to be able to read these results, but instead I want to focus in on the fact that the unbin results are provided as a 24-dimensional data set on Zenodo with code to be able to manipulate it on GitLab. And so the really impressive thing about this result, and I encourage you all to go and try this out, I actually did it myself as well, is you can actually do measurements of new observables that are not present in the original paper. So basically, by releasing the data in this way, you can actually get new differential measurements, for example, of tau2-1 for one of the jets in the event, or of the delta R between the dilepton system and a jet in the other example. OK, so finally, in my last couple minutes, I want to talk about how we're using machine learning to enhance the search for BSM physics with anomaly detection. And so there's a broad landscape of ways we can do BSM searches. On one side, fully supervised, where we know exactly what signal we're looking for, and we have like full label information, let's say, to train classifiers. And on the other side, we have the fully unsupervised. So we have no labels. An example of this is using an autoencoder, so where we train it to compress data and then reconstruct the original data. And the idea is that if the reconstructed data is far from the original data, then we can flag that data as anomalous and try to look for new physics using these anomalous events. So how this works in CMS is that there's a search for anomalies in dijet events. And specifically, large radius jets are selected with some basic selection criteria. Then 5 different anomaly detection techniques are applied to this data. That range from fully unsupervised to semi-supervised and even hybrid methods. I'll focus right now on just one of them, which is this variational autoencoder, so it's fully unsupervised. After these methods are applied, the anomaly scores are computed for each of them. A cut is applied to keep the 1% most anomalous events. And then with these events, we can actually perform a bump hunt. So look at the dijet invariant mass and see if we see any resonances in the mass. So the takeaway is just in this plot shown on the bottom here, which is that for a wide variety of benchmark signals, because of course we need to interpret our results somehow, even though these are model-independent searches, For a broad range of signals, what we see is an improvement in cross-section needed for a 5 sigma discovery of that signal compared to the inclusive digit search. And actually, the improvement is by up to a factor of 7. So this shows you how powerful this can be when you're not sure what signal you're looking for. Atlas is also applying anomaly detection in the form of an autoencoder applied to this physics-informed representation of the data. Similarly, you take the most anomalous events and you can perform a bump hunt. And what's really interesting about this result is that it performs this search not only in the digit final state, but also in the basically 9 different final states of different pairs of objects, including jets and photons and B jets and electrons. And there we can get model-independent limits in a variety of ways. Okay, thanks. Okay, I don't have time to talk about this too much, but just really quickly say that anomaly detection is also being applied in the level 1 trigger and actually is currently taking data. And what's really interesting about this is we're collecting new data that wouldn't have been selected by any other level 1 trigger. If you have questions, you can ask me more about this after. And then, again, don't have time to talk about this, but one really cool method, which is called this normalized autoencoder, because sometimes these autoencoders can be too good at reconstructing signal, meaning that signal is not flagged as anomalous. So this normalized autoencoder approach is designed to mitigate this issue and align the low reconstruction error phase space with the background phase space as well as possible. Again, the takeaway I want you to get here is that all of this signal with the traditional training would be lost due to not having high enough signal reconstruction error. And then if you apply this normalized autoencoder training, which I don't have time to discuss, you can actually mitigate this significantly. So being able to flag much more signal events as anomalous. Okay, so to summarize, there's a dizzying array of machine learning opportunities, innovations, and applications in LHC experiments which are directly impacting our physics results today. And there's a lot of new ideas that rethink on the best way to apply machine learning. And nowadays, we're not only concerned with performance, but also robustness, interpretability, and sensitivity to modeling uncertainties. And there's many use cases beyond classification, including simulation, unfolding, and anomaly detection. And machine learning is enabling new searches and measurements that were impossible before. So thank you.
So questions? So please stand up if you have a question so that we can see you.
Hi, very nice summary. With regard to the fast simulation, is there any way of telling how much extra events you can usefully generate this way? I mean, for instance, if you start with 10 fully simulated events, you're not going to be able to produce meaningfully 1 million fast simulations, presumably. So how can you tell when you should not carry on anymore?
Yes, that's a good question. So essentially, it's, what is the statistical extrapolation power that we can get? Is it a factor of 10? Is it a factor of 100? There were some really interesting studies done on this exact question, basically seeing at what level can you meaningfully extrapolate. I don't know the answer off the top of my head, so I can look this up, but I can point you to some interesting studies maybe offline. But I would say one of the things that is interesting is that we often don't necessarily need it to be, let's put it this way. We can train the model once and then apply it in a variety of different physics samples. So even though in the physics samples we need hundreds of billions of events, it's not all the same physics processes. So in the sense of like each individual, the statistics for each individual sample is much lower than hundreds of billions. So I think we can definitely satisfy the needs of individual analyses that way.
Yeah.
Thanks a lot over here.
Yeah.
Thanks a lot for this very impressive set of results and of things that one can improve in this way. However, there is one aspect where I'm always a bit skeptical about, and this is what the promises about the anomaly detection part. I mean, I think as long as your anomaly detection analysis tells you that you have no evidence for an anomaly, then everybody is happy, and you go ahead and publish the limits, and everybody is happy with that. But suppose you do find something that deviates from the standard model. I mean, we know how things work in Atlas and CMS, And I think it's very unlikely that you will come out with something and say, oh, we have no idea what this is, but it differs from the standard model by 5 sigma. We publish it anyway and say we have discovered something. So I think this is not going to happen. So what is the plan how to deal with if your anomaly detection methods really come up with an anomaly? What will be the next steps then?
Yeah, let me just say first, I would love to have this problem.
Yes.
But I think that in the same way as we apply, our blinding strategy, in the same way that we do other analyses, we can still apply the same principles. One thing that I think would be really important immediately afterward is to characterize the signal. Basically characterize what other features, besides just having a high anomaly score, what other features are relevant to that, that are making it have a high anomaly score. And then I am sure we would be able to kind of, based on that, come up with a candidate hypothesis, candidate new physics model that we could then see how consistent is this anomaly with this new physics signal, and then perhaps design a standard analysis for that. Of course, that would mean maybe needing more data, maybe needing to build a trigger specifically for that signal. But I certainly think that would be the next step. Certainly, I think we wouldn't be able to claim discovery of new physics without specifying what that new physics is. So I think there would be a program that would be started by this kind of suggestion of a discovery. Yeah.
Okay, thank you.
Another quick question?
Maybe one very quick. Also, it's kind of inspired from the anomaly detection. So as far as you work with convolutional neural network, for instance, it's easy to visualize and understand why your weights works the way it works. But if you, for example, use a recursive one, as far as I know, it's kind of hard to actually understand what's going on there. So my question is, does the collaboration publish and trust results without fully understanding why the anomaly detector is doing what it's doing in all these weights?
Yes, good question. So I think there are model interpretability techniques that we can apply to models, even if they're recurrent neural networks or graph neural networks, that would tell us basically which are the most important features that give me a high anomaly score. So I do think that we would want to apply those techniques immediately. I mean, we're already actually doing it in some different situations to try to see what are we sensitive to, especially on the trigger, right? We'd like to know what are we most sensitive to right now for these anomaly detection methods we're putting in the trigger, because obviously that contributes to rate, and so we want to minimize that. So yeah, I think there are techniques we can apply there, essentially. Like layer-wise relevance propagation is one that can be applied to these other methods. Yeah.
I would like to
Okay,
ask.
very quick.
Yeah.
Could you go back to your simulation of JON? You were showing that you could, you didn't need to use JON and that you could somehow simulate JON, I think is what you were saying.
Yes.
But in that left plot, it doesn't look very good. I mean, what is your criteria, I guess, for saying that you're satisfied with what you're doing? There looks like there's some difference on the one on the left and the bottom.
Yes.
It doesn't look the same, is what I'm saying.
Yes, I agree. It's not, the simulation isn't perfect necessarily. The replication in all the high dimensional feature space isn't perfect. Actually, there is a paper describing exactly like the kinds of metrics that we can use. It's called evaluation metrics for high energy physics, so encourage you to look it up. But yes, you're completely right. We need to kind of work on defining exactly when a generative model is good enough for our purposes. And again, that depends on the sample sizes that we need and basically what are the relevant features for a particular application. And so, yeah, you're totally right. In this particular plot, it's maybe not immediately obvious that this is good enough, but depending on the application, it might be some small 1% effect in your final observable, which would be then considered good enough.
Okay, so let's thank our speaker again.
Yeah.
Our next speaker is Vitor de Souza from University of Sao Paulo, and they are going to switch now to astrophysics, and he's going to speak about multimessengers.
Okay, so thanks a lot for the organizers for the opportunity to bring you news from the outer world, from outside this planet. I'm going to speak about multimessenger astrophysics. And this slide fits nature. Nature fits inside these slides very well. I used the fundamental definitions of energy to draw this axis of energy, frequency, temperature, mass, and wavelengths. Oops. And I invite you now to pick up a region that you work. So you can choose the axis you prefer, either energy or the characteristic mass of the particle you look for, and you can select here the range that your phenomena fits. And the universe is very generous to us, sending us messengers from all these energies. I'm going to show the sequence, the traditional sequence of slides, seen from energy, very low energy to the highest energies. The sky maps we can make with different instruments, looking at this radiation that tells us very different things with different structures emitted by different objects that reveals us very different things from the universe, going in light up to gamma rays, the highest energetic radiation that we can get from the universe. But doesn't stay that, we can go for other types of particles as well, including neutrinos, as we are going to speak further along this talk, and charged particles as well. To the highest energetic particles we know in the universe, which are measured by the Pierre Roget Observatory. This is the sky map of particles with energy above 10 to the 19 electron volts. But not to forget our last messenger, last discovered, gravitational waves. We are going to speak more about this map as well, but with a very high energetic release in each of the events. So putting all of these together, we can see all the maps with the energy scale here, but a little bit more massed, not really organized in energy. We usually divide this energy range into two regimes, one that can be explained by the temperature of the object that is emitting, and the highest energy part that cannot be explained by the temperature, no non-thermal emission. And I would like you to remind that until the end of this presentation that all of this emission, that is exactly what we call nowadays multimessenger, should have the same mechanism operating behind them. They should be produced together. While here this is not true, but this, the upper part, there should be correlations between the emissions into these different messengers that we are starting to probe now, that we are starting to study nowadays. So I'm going to speak a little bit about each one of these messengers shown here: neutrinos, gamma rays, cosmic rays, and gravitational waves. And why should we do that? This is my answer to what I do every day, because multimessenger astrophysics probes the highest energetic phenomena in the universe. You are going to see that along the talk, and also because it highlights the physics of the four forces, meaning that the four forces we use in nature, they really have to be applied together. You cannot differentiate, you cannot separate these forces. I'm going to show examples of that. It searches for dark components, mainly dark matter, as you see. It teaches us acceleration mechanisms that we don't really know how they work in these objects, and tests our knowledge of the current physics we know. One of the examples is the tests of Lorentz invariance violation that are very well done with these messengers that have the highest energies, as shown here, and come from very far away. So very small phenomena are amplified by the highest energies and by the distance this particle travels, being detected here. So here I invite you now to remember which region of the plot you selected and compare with the gamma rays we get from the universe, which are the highest energetic radiation we know exists in the universe, or the charged particles, again, the highest energetic particles. And if you don't work with multimessenger astrophysics, I bet your energy range is well below these two blue regions that I selected here. The second because that I wrote there is because it's the home of the four forces. This is an artistic drawing of an active galactic nuclei with a supermassive black hole in the middle, and this accretion disk accreting lots of matter around it, spinning, and exactly because it's spinning creates these jets, such as that the gravitational energy is converted into kinetic energy, leaving these jets, but also into electromagnetic energy that is used to accelerate these particles, charged particles. The particles then interact and decay, generating neutrinos and gamma rays, which are the most direct signal we can get from these objects. But that's why I call it the home of the four forces, because these four forces, they need to be applied together. This is where exactly they started to fail when we started to use them all together, and we need a better theory, a better explanation to study all these phenomena here that can be probed and studied with these messengers. So I'm going to show slides that are a selection of results. Most of them were presented here during the last days, but some were not. That was the challenge that the organizers gave to me, also to include main results that were published recently. I'm going to focus on the moot aspect, meaning that I'm going to show experiments that have other important results, but I'm not going to show them if they are not correlated with a second messenger. And of course, it's a biased and incomplete view of the field. I'm going to start with neutrinos. We had a very nice talk this morning from Lulu about neutrinos as well. This is probably the definition of multi-message nowadays, which is the sky map of our galaxy published by the ICHEP collaboration. You can see here the data. And it's really, it is really multi-message map because it starts here with a gamma rays detected by FERM, from which you can predict the amount of pi zeros that was needed to produce this map, and compare with the gamma ray, the neutrino emissions measured by IceCube. And we saw also in the presentation from Lisa in this conference that there is no evidence of correlation with non-TeV gamma ray source from this map, which is a surprise. You expected that the main emission from neutrinos should be correlated with gamma rays exactly because the most simple models imply that the mechanism of production is the same. But not only the galactic neutrinos, IceCube has also important results for extragalactic neutrinos. This was, in this conference, the first time I saw this new map from IceCube, still labeled as preliminary. The previous map that I showed in the first slides had only 3 sources, but now they have many sources. We are, of course, expecting for the paper to be published soon, I hope. And I would like to highlight this galaxy, which is a very known galaxy, NGC 1068, because it has no counterpart again in TeV emissions. So another surprise that is telling us something about the mechanisms operating in this mechanism. I'm going to tell more about correlation as well. The good news is that IceCube is upgrading. It's increasing the size of detection, but not only, it's also installing top detectors that helps the experiment to remove noise and get us more sources in the TeV neutrino sky. Very recent, I'm sorry this slide is a little bit old, but the reference here, there was a presentation in this conference as well from Chem3Net ARCA, in which they detected this extraordinary event. This is the number of photomultipliers as a function of the zenith angle. This event is very far away from most of the events they get, and it's very energetic. It hit Nature News some days ago. And if you go in the slides of this conference, you are going to see that this event corresponds to at least 10 PeV neutrinos. And this is going to be probably the most energetic neutrino ever seen. We are also expecting to see the paper, and the consequences of this event are going to be huge. Cosmic rays, starting with the Pierre Roget Observatory, running in Argentina for more than 20 years. We saw from Alexei a study of the correlation of the ultra-high energy cosmic rays with ice cube and Antares neutrinos. This is the map Alexei showed in this conference. I'm not going to have time to go into the details of the map, but the conclusion he showed was that there is no correlation between extragalactic cosmic ray and neutrinos found so far. So again, high energy energetic neutrinos do not correlate with ultra-high energy particles, which in our standard model should be the particles accelerated to generate these neutrinos at the highest energies. And in a second paper, in another paper, the Pierre collaboration published also a study of trying to find high energy photons with correlation with gravitational waves, and again, no correlation was found. Another source that has been a prototype of multi-messenger is Centaurus A. Centaurus A is a radio galaxy very nearby. Even in the traditional astronomy, it's considered a multi-messenger because it's visible in several wavelengths. But not only, there is also the famous detection by the Hess Observatory, where they saw it's a TV source as well. And there are hints from the Pierre Observatory that there is an excess in the direction of Centaurus A. This is a scan that the collaboration did in energy and the search angle for this correlation. And there are 215 events observed when 152 would be expected from isotropy, a post-trial p-value of 4.5 10 to the minus 5. It's not a discovery of a source, but it's a very strong hint that this source could be producing ultra-high energy cosmic rays. The good news is that the observatory, the Pierre Observatory, is also upgrading. Alexei showed us the installation of new electronics, new PMTs, and more important, 2 different kinds of detectors on top of the water Cherenkov tank, radio antennas and scintillators. And the importance of that is that we will allow the data analysis to select the low charge events, mainly protons, and the protons deviate less in the magnetic fields, so it's going to be easier to point back to the source that are emitting them, because the large charge, the nuclei, are more deviated and make the distinction of the source much more harder. Galactic cosmic rays, we have AMS. AMS is this detector working in the International Space Station, detecting many kinds of particles and nuclei. I'm going to show just one plot, which is usually the highlight from an AMS. Andrei showed us here in this conference the positron flux as a function of energy. And some years ago, the traditional prediction was this gray band here. So no second bump was expected, but AMS showed that some time ago that there is a second bump, unavoidable from the data to see that. And then that started a new campaign of theories to search for what could be the second component, and the 2 models can fit. One model based on pulsars and the second model based on dark matter. Andrei showed a long list of reference of the 2 models. I really recommend you go to see his slides, and he really shows how both models can describe this data. But of course, we are looking forward to see how this is looking like when we get more data here. And Andrei also showed this plot trying to convince us that in 6 years, so the projection of the data for 2030, we are going to have points here, the highest energies, that maybe could distinguish between the 2 models. But I didn't see from his presentation any test statistics of including these points and being able to distinguish between the 2 models, which would be very good to have besides the visual impression that these points could help us distinguish a dark matter model from a standard astrophysical source. Gamma rays. So the most important gamma ray detector in operation is probably the Fermi-LAT. It has been working for decades now, and it's very important because it's a now sky monitor. There is no successor of Fermi-LAT programmed, or at least in an advanced phase, and not having a satellite detecting gamma rays is going to be a big loss for the area. It's so important that it was indeed the responsible for detecting these very famous binary neutron star mergers. So the first gravitational wave event shown here in this map that has a counterpart in gamma rays. Not only Fermi, recently LHAASO started operation. LHAASO is a multi-detector, but specifically running a water-Cherenkov tank as well that detect gamma rays. LHAASO observed 90 sources shown here in this map. Among them, 32 were discovered in the TeV sky, 43 above 100 TeV, so the very highest energetic gamma rays. And 7 of these sources are considered dark, but dark here means that they were not known in other wavelengths. So they were really discoveries first in TeV emission. And here you see the map from LHAASO. LHAASO is very important because it goes very high in energy, so it can detect very high energetic gamma rays, but also because it's a wide field of view, so it can monitor the sky. And then the CTA observatory or the Cherenkov telescopes running a different technique that observes the air shower and then can pinpoint the source much better, as shown here by the angular resolution as a function of energy. You have in black and red the simulations for the CTAO northern array and southern array. CTAO is going to have many telescopes running in the Canarian Islands and many telescopes running in Chile. And you can compare that to the satellites and to the wide field of view detectors. You can see how CTA can make an improvement in angular resolution, therefore make precision measurements. Not only that, the range of energy that CTAO is going to measure includes both extremes, include the satellites and include the wide field of view detectors. So it's going to be only one instrument, therefore with only one systematics measuring the full energy range. Besides that, CTA also has several modes of observation. It can point one telescope because it has dozens of telescopes. It can point to one telescope next to the other and make a survey of a large area, for instance, the galactic plane, but still keep some other telescopes making monitoring of different sources that are interesting or something are happening in other wavelengths. You can see the power that CTAO is going to have by looking this number of sources as a function of the years. You can see that when a new technique or a new set of instruments start to operate, the number of sources increase a lot. So when the first generation of Cherenkov telescopes started to run here in 2005, you see this increase. Then the wide field of view detectors, you see another very abrupt increase. And all we know about the TeV sky is based on 270 sources. There is nothing. It's very few sources that we know of. It's 270, and CTAO will bring that to above 1,000 sources measured in very full detail in a few years. The last messenger, I'm not going to speak much because we are going to have a very good talk from Samaya still in this session. I know it's a very good talk because I saw the slides I read when preparing my talk. She's certainly going to explain all about this plot of the mergers. But we also saw from Nicolas in the sessions before, in the last days, the representation of all the mergers. And mainly the ones here, they should, or at least our theory predicts that they would produce counterparts, at least electromagnetic counterparts. But only one of them, this famous one, first detected by Fermi and then later by the Cherenkov telescopes on ground, has. So the other ones do not have, and we don't really understand why they are not visible in other wavelengths. We know we are in a transition phase. They are starting to run the run 4 of this combined experiment, and the number of events is going to increase a lot, so we expect to have many multi-messenger events for this run 4 in the next years. Of course, we are also very hopeful about the future experiments, Einstein and Lisa, and this plot of the gravitational wave spectrum shows which what kind of mergers could be detected by different techniques, and tries to argue that the space interferometers would see some objects that probably could produce more messengers besides gravitational waves, and therefore be studied in more details. I want to finish in the last seconds I have, reminding you the US 2020 Decadal Survey, having as priority 3 bullet points, and showing very explicitly that multi-messenger is one of them. So probe nature of black holes and neutron stars. But not only in the bullet point here, the last paragraph of this chapter highlights that even more, saying that explicitly multi-messenger program is needed to advance our knowledge in this field. And also the European astroparticle physics strategy in this report, in this roadmap, has a recommendation of spending all messengers. So the community is pretty much convinced that we are only going to advance our knowledge in this, how these objects accelerate particles and how this emission happens, if we have all messengers measured in the next years. I'll let you with my answers here of why we should study it, and I'll just summarize by saying that what I try to show you is that there are many things in this new field, called multi-messengers, sometimes a little bit fuzzy, not very well defined, the boundary is not well defined, is that there are many things we don't understand. There are many things challenging our standard models of emission in these objects. Some predictions say we should have neutrinos and gamma rays. We don't find the gamma rays. Some predictions says we should have gravitational waves and gamma rays. We don't find the gamma rays. This is a characteristic of a new field that needs more data. But what I also try to show you is that new data is coming. So all observatories running today are upgrading. That guarantees the continuation, and new experiments are being planned, given the importance of understanding this phenomenon. It's certainly going to be a multi-bright and a multi-challenger future, so please join us. Thanks a lot.
Thank you, Victor, for this very nice overview. Are there any questions? Oh, there's one.
Thank you for this very interesting talk. So what I learned from it is that really there seem to be, while it's low statistics, fewer of these correlations between different messengers than what we expect. Is there any possible explanation for this, or what would it mean if this actually, if this continues to be the case and is not just a consequence of, you know, still those statistics or so? So is there a model which would, you know, explain that?
So there are several models trying to explain specific measurements. For instance, NGC 1068 that was seen in neutrinos, but is not seen in gamma ray. You can do that by making a very dense torus that absorbs the gamma rays but do not absorb the neutrinos. But you know history. You cannot make one model for each source, right? So if it's only this source in our statistics, that's fine. But if other sources start to appear with the same characteristics, it shows that the problem is not the statistics. Then the problem is we need to review our standard model and see how these objects are formed. It's either the acceleration mechanism that is not properly understood, or the environment. The environment is as important as the acceleration mechanism.
In terms of absorption, for example, that part of the, yeah. When would we be at a stage where there's a real challenge to the picture?
I think it's already a big challenge to the picture. These events I highlighted here, and others I did not show, very explicitly says that the multi-messenger data is put in our standard model of these accelerators in challenge. Another example I could give is the amount of, it was also presented here, the amount of heavy nuclei we detect, or the ratio from cosmic rays that AMS detected. There are many, many points that have been challenged recently.
There was a question there.
Yeah, very interesting talk. When you discussed the positron excess in AMS, you presented that it can be explained by pulsars or dark matter. Now, as a particle physicist, sorry for I'm biased, I listen to that and I hear it can be explained by standard model or beyond the standard model. Now, if something can be explained by standard model, beyond the standard model is not needed. So maybe I missed something about that.
Maybe what I can add is that by the time the data came, the models for pulsars were not so developed to explain this data yet. So there was a stage in which you could not say that the standard model was explaining, because we needed to develop the pulsar models of emission and also the propagation of cosmic rays a little bit further, and then it could explain.
Thanks.
Hi.
Go ahead.
Question about neutrinos. So would you like to tell more about the interest in multi-messenger with detecting like MeV scale, 10 MeV scale neutrinos, so very lower energy than the one you mostly talked about. So essentially, if I have a MeV scale neutrino, a detector which is sensitive to this kind of neutrinos, which kind of sources beside the supernova should I investigate for multi-messenger?
Very good question. So if you go low in energy, you are limiting your range to the nearby universe, and then the contribution should be mainly supernovas. And this is what probably this map from IceCube tries to correlate, because you are only expecting the main emission. You can also have emission from the propagation of cosmic rays interacting in the clouds and then making. But I think this is more understood than the emission in supernovas. My guess.
There is one more question there.
Thanks for your nice talk. So my question is also about the correlation among messengers. So you mentioned that currently there's no correlation among them has been found. So, but with the events accumulated, do you think it is hopeful to find, at least for some sources, that these messengers can be correlated?
Yeah, I think as Carl Sagan said, the lack of evidence does not mean that we are not going to find it, or he put it in a better way than that. So there is no evidence. That doesn't mean that we are not going to find evidence in the future, right? It's clear that we need more statistics, as was said before. Yeah. So we need to wait this map from IceCube to be more populated. If you look the map again, we need more statistics there for sure. If you compare the map of neutrinos with the map from gamma rays, you can easily see how the statistics is not compatible, because we have a map of gamma rays that is full and a map of neutrino that you only see the boundaries of the emission. But we need to wait.
Yeah, thank you.
Okay, let's thank Vitor again.
So our next speaker is Felipe Andrade-Oliveira, who will be talking about observational cosmology and measuring the late universe.
Thank you, thank you. Hello, everyone. It's a big pleasure to be here to talk about some recent progress in observational cosmology. I want to stress some experiments regarding the late universe. So in this talk here, I'm more focused on the physics of the growth of structure and the physics of the dark energy. So for starting, let me set what we know about the universe. During the last decades, we've been looking for the universe from several different perspectives. We look at the cosmic microwave background. We look for the supernovae. We measure the structure formation. And what all the different perspectives have in common is we got some consensus model for the universe. In this consensus budget, we put the flat universe with some recent process of accelerating expansion, defying the gravity ordinary laws. Also, the universe seems to be homogeneous and isotropic, which means that the physics that we observe in this side of the sky is the same physics that we observe in the other side, even though for small scales we can see some structures and difference, but they are all statistical. And in these large scales, where we can observe this homogeneity and isotropy, the main force is the gravity. And as far as we could test until now, as far as our experiments could go, the best theory, or the simplest one, is the general relativity. Also, in this model, we have some different components than one could expect from the physics on Earth. The first one is the dark energy that's driving this acceleration. The simplest model of the dark energy is the cosmological constant. And the second one is the cold dark matter. That's something that has some gravitational action and help us to make the structures cohesive, but has some very different properties than the matter that you can find in your periodic table. Besides that, more recently, we are facing some tensions in some of these models some of the models of this, some of the parameters of this model. This is leading us to try to approach some questions. The questions that we can actually try to address using cosmological surveys are if the late universe and the early universe has the same consistent story. This means that we can connect the tips of the universe with a single model and connect this in time. The second one is from the smooth universe and the structure that we can see forming in the universe. If our model is enough, we could explain both how the universe is expanding, how was the past, and how the galaxies and the superclusters and cluster of galaxies are forming. And finally, and maybe the most challenging question is, what is the nature of the dark energy? What is the nature of this totally new fluid that is anti-gravitational in the sense of a new Newtonian gravitation, and that is driving in the large scale this accelerated expansion? So nowadays we have several experiments trying to address these questions, and I'm going to stress the nice work of two of them. So the first one, the Dark Energy Survey, is an imaging survey. So it tries to capture a huge number of images of galaxies, and they try to detect their properties using the best camera produced by everyone in the history until this exactly moment, when now we are going to have the LSST camera. And it tries to map the structure of the universe, collecting galaxies from an area of 5,000 degrees squared, which more or less 1/8 of the full sky, and detecting the galaxies for the survey for almost 6 years. So this year, we are publishing our final results with all the data, but they are still not public. They are still blinded for us, even for us. And I will show the latest generation of results, which is very interesting. So the Dark Energy Survey is also able to produce the largest map of dark matter distribution so far, because it can measure the shape of galaxies, and it can measure how the intervening matter, is changing the shape of this distant galaxy field. So in this side, we have another survey. It's the Dark Energy Spectroscopic Instrument. We have not been very creative with the names, DES and DESI. They are very similar. But the main feature of this new experiment is that it collects very detailed information about the redshift of galaxies. And it does this using 5,000 spectroscopic eyes. So we have robots that can point from the precision of 1 micron, from the precision that is smaller than the size of your blood cells. And we use this to point for galaxy fields and covering more or less 1/3 of the sky in the north. The operations has just started, and it's been a very thrilling process. Even with a big fire in the telescope, close to the telescope in Arizona and some other issues, in 1 year we could collect more spectrum, more high-quality data than all the other experiments together until DESI. So what we want to do with all this data is probing the expansion. So we need some reference, and we have something that we can use for measuring the distance. And we used to use the distance redshift relation. So in this relation here is encoded our cosmology, and we can infer the properties of the cosmos comparing objects that we know their intrinsic luminosity, or at least that we can calibrate in the case of the Cepheids, that we can calibrate the luminosity given the period of oscillations. And also we can calibrate the supernova using also the Cepheids that are not very far away in the same range, and we can look further using luminosity and distance calibration with the magnitude of the supernova 1A. The main challenge here in this kind of proposal is set the proper calibration, because one calibration depends on the other step, and classify properly, because in practice, what you see in your survey is just a spot of light, and it's not trivial to understand if this is a supernova 1A or other kind of supernova or other different kind of object. In the newest front, since 2017, we could develop a new method called the standard sirens. This was proposed in the 80s, but it was only made possible recently. And in this case, the luminosity is given for you, but you need to find some way to determine, to find the proper redshift of the event. So the two ways of doing this is the first one, trying to look at the electromagnetic counterpart in your survey. That's a really hard task. Or looking for a catalog of galaxies in the same region, and try to cross-correlating the redshift of the galaxies and your distance from the GW signal. This electromagnetic counterpart was done only once in the history, and we are trying to improve methods in order to find more and more counterparts. So the other way of probing the expansion is using standard ruler. Standard ruler, in the case of the cosmology, is something that's not given quite for free. We need to extract this from statistics property. So in this case, the case of the DESI survey, for instance, we collect something called BAO. A BAO is related, it's the baryon acoustic oscillations, and it's related on how in the very beginning of the universe, right after the inflation, we had the fluctuation fields, and this creates some pressure sound waves that propagate. We know that when the universe reached a very young age of 400,000 years, it gets cold enough so the photons and the baryon matter start to decoupling to each other. This releases the CMB, and the peaks of CMB is also related to this acoustic wave. but it also it also freezes this wave in the matter field. And we can observe, using correlation function, we can observe this peak of correlation, this local excess of probability of finding another galaxy that is related to the BAO. It's called the BAO feature. And the position of this peak is giving for you what we call a standard rule, that you can compare your observation and your theory. Finally, in the case of the dark energy survey, we can observe the cosmic shear. And the dark energy survey is currently the best experiment of doing this, sharing the first position with several competent ideas, of course. But the cosmic shear comes from the fact that we can observe very distant galaxies, and the shape of the galaxies, in this case you need to measure the shape of the galaxies, is distorted by all the matter perturbations, all the structures that you have in your ray of light. This is a small distortion. This is really, really small, and we need to collect hundreds of millions of galaxies so we can get some useful signal. These same fields that distorting the light and the shapes of the distant galaxies is also an environment that can form more galaxies. And we can use these visible galaxies in the dark matter halos in order to also setting how the positions are correlated. And this is directly related to the gravity. Finally, these halos and these galaxies that are distorting these distant galaxies and the shape of these distant galaxies are also related, and we can using a third kind of correlation. So this method is quite sensitive to how much matter you have in the universe, and also how clustered is the universe, how clumping it is. And we are using this quantity S8 in order to quantify these properties. So results from the dark energy year 3 is the first one is that using all this correlation, using 110 million galaxies, we could determine the S8 with a precision similar to the CMB experiments that are the most precise ones. We see some difference, and in the other surveys, we can also see that this method is obtained a lower value, but looking for the error bars and looking for how close they are to each other, we cannot say that this is properly attention, and we need more data in order to get to some conclusion. The DS also has these programs of supernova, and we collected the largest compilation and the compilation of supernova that's giving the most stringent constraints. The DS supernova is also confirmed that accelerating expansion with 5.2 sigma of credible level. And maybe the most interesting for this audience highlights is that the supernova data is slightly disfavor a cosmological constant. So here in this edge is what you would expect if the universe is just cosmological constant with the dark energy not evolving, and the data is giving some small preference to other kind of dynamical model parameterized by this relation here. So finally, going to the most recent results, we have the DESI, the spectroscopic instruments. And this first year, we use 6 million of spectra from different kind of objects. And DESI is very, very skillful in constraining how fast the universe is expanding. So DESI got to this result here that's similar to what you can obtain with the cosmic microwave background methods. And the DESI is confirmed some good level of tension between the supernova results, and that's a local measurement, and between this indirect measurement, but in a very early universe. This tension accounts for 4 sigma. Other important topic is that DESI is also very sensitive to neutrinos, and I will pass super quickly from this slide, but this is how the neutrino affects the structure formation, and DESI is constraining the sum of the massive neutrinos in 0.07, but this is quite dependent on the model, because we are actually measuring correlation functions from the cosmology. Finally, this is super interesting because DESI also combined their results with the supernova data and using the same kind of parameterization. And for the first time, we can see a good level of tension between what is a universe with lambda CDM and the universe with some kind of other exotically dark energy. We cannot conclude anything right now because it's just the first generation of the data, and we need to improve way more these constraints. But this is very exciting. So here is the status of the cosmological tension. For SE8, for how clustering the universe, experiments that are dealing with the structure formation and CMB are slightly different, but not quite in tension. But on the other hand, the experiments that are measuring directly the recession of objects, like the supernovae or the tip of a red giant branch, are obtained something that's quite different with the indirect estimate. But for one hand, this is indirect, but this is quite precise and not dependent on calibration. And this is direct, but it depends on calibration. So this is the big discussion that we are having in our community. New results are coming soon. In the end of this year, we plan to provide our final legacy results from the DES. The DES year 3 is also coming with new results and constraining growth of structure and the new constraints in the dark energy with way more data. And also, we'll hope to find more electromagnetic counterparts and use the distance from GW in order to give some opinion about the 8-knot tension. My final remark here is that after 25 years of the lambda CDM, it's still a very useful description of the history of the universe. We have 6 basic parameters, but we have a tension in a single one. We need to understand if this tension comes from systematic or some other kind of effect, maybe new physics, but it's too early to say. We see some small difference on how clustered is the universe, and we start to observe some small evidence of a non-cosmological constant. For the high-energy physics community, I want to stress that from this kind of experiments, we can bound the massive, we can help unbound the masses of neutrino. We can also help to bound how is the hierarchy of neutrinos. If we find something that's not a cosmological constant, this may be something very interesting for the community. But if we confirm with more details that the universe is quite lambda, it will bring other kind of questions regarding the cosmological constant problems. And we also have the dark matter astrophysics that I didn't approach here, but it can work together with both communities. This new generation of experiment will advance in our vision of the universe, their components, and the dark energy. So thank you so much.
So, questions?
Sorry. Thank you very much for this interesting talk. I heard that this tension was caused by that the indirect measurements observed dust. Is that correct? Have you checked that?
Yes. I guess it really depends on which community you heard, because I've been working in both communities, and it doesn't seem something like so simple for the local measurement. If you have some dust in the intervening in the supernovae, you can see some signature in the spectrum, some signature in the light curve, and at now it doesn't seem something like this. But I can ensure that people are really investigating and try to look for other kind of systematics and try to decide on which method is correct. Hopefully, both are incorrect, both are correct, and we actually have some new interesting physics, but we need to be very pragmatic.
Okay. And the other question is, you didn't say much about the new experiments, like the LSST Rubin, the other ones.
Oh, thank you so much for your question. I really would love to talk more about this, but the time was limited. So LSST is going to make a movie of the sky. It's going to improve way more the efforts that we could gather with the dark energy survey. It will cover half of the sky every 3 days. So we not only will have deeper observations, more precise observations, but we also are going to have some dynamical view of the universe. So it's going to be very breakthrough-ish. I'm super proud of being part of the team. And it's going to start next year. Our camera is ready on the mountain, and we are looking forward for new results. Thank you for your question.
Hi, hello. Yeah, very nice. Can I?
Okay.
Yeah. Very nice talk here. Hi. I have a question to the technique of observation in general. There was a phase where we had these space-based telescopes, but now you are essentially counting on the Earth-based telescopes. What is the advantage of the Earth-based telescopes with respect to the space-based ones?
They are cheaper.
Cheaper, okay. Yeah.
Okay, but we can build very larger mirrors in the ground-based telescope. They are easy to upgrade. We can construct new instruments and adapt for the next generations of the ground telescope. I didn't say much about space telescope given the time, but we are having also the Euclid on space. We also have Roman. And actually, our expectation is that things are going to work together. LSSTs also gain a lot of information by the observations that we don't have the atmosphere. Who needs atmosphere? No, I'm just kidding.
Thank you.
Thank you.
Yeah,
many thanks. Can you say anything about explanations for the tensions that you're starting to observe with the cosmological constant?
It's super hard to find people from here, now I understand. So what is the question? Sorry.
Thanks very much. So you explained that there's some tensions with respect to a model purely explained by the cosmological constant. Could you speculate anything about models which can potentially explain this?
Yes, indeed. We are doing a very thoroughly and big study in the dark energy survey, for instance. Also working with different kinds of gravity and other kind of effects, neutrinos, etc. I didn't bring any results because they are not quite conclusive. We still didn't reach the precision to rule out general relativity or something, or maybe general relativity is just the answer for the large-scale structure. But yes, definitely there's a lot of room for working on this. My work as observational cosmologist is to make this room smaller so we can have less possibility. This is my fun.
When you present results on S8, I hope you would also include the results from other galaxy surveys like HSC.
Yeah. Sorry, yes. Yes, it's not only HSC, but also the Kilo Degree Survey. They are doing excellent service. And indeed, we have some combining constraint, but it's just a lot of ground to cover, and they are amazing experiments. Thank you for your comment.
Thank you. So I just wanted to ask, when you use the neutrinos to probe the curvature of space-time, do you use solely the directional information of neutrinos, or do you also take into consideration some flavor or oscillation due to the time dilation?
This is a very good question. We actually are not sensitive to a lot of the properties of neutrino. So what we can measure properly is the sum of the massive the sum of the masses of neutrino, because this has an effect that smooths out the structures, the small scale structures. With this smoothing of the small scale structure, we can see this very clearly in our power spectrum. So the cosmological experiments has some very limited ability to measure some of the neutrino properties, but we can work together in order to have better constraints for the whole physics community. Thank you.
Okay, so let us thank our speaker again and move on to the next.
So our next speaker is Samaya Nissanke, and she's going to speak everything we want to know about gravitational waves.
Thank you very much. So, dobre dien. And I'd like to thank the organizers, firstly, for inviting me. In the next 20-25 minutes, what I hope to do is outline the challenges and opportunities for current as well as future gravitational wave detectors in the next 20 years. So, in the last 9 years, with the LIGO and Virgo detectors, we have observed at least 90 compact object mergers during 3 science runs. So what I'm showing here in this schema, on the vertical axis is the masses in solar masses. The horizontal axis does not have any significance, and the blue and the orange bubbles represent those black hole progenitors as well as remnants, and neutron star progenitors as well as remnants that have been observed in gravitational waves. And you can compare this with the red and yellow bubbles, which are the previously inferred masses for black holes and neutron stars from radio and X-ray observations. And as we heard, in the last year, we began our 4th science run, where we have now announced at least 118 significant candidates, including an exceptional GW 230529, a published event, one published event from the 4th science run. Now, there are several things I'd like to point out. Number one, that we're uncovering this diversity in the fundamental properties of these black holes and neutron stars. Secondly, there remain open questions as to what is the nature of the progenitor as well as remnant of some of these low-mass neutron star black hole mergers, as well as the existence of previously hypothesized mass gaps. Thirdly, there is a handful of neutron star black hole mergers where at least one of the objects has matter in the form of a neutron star, and where we may expect electromagnetic emission arising from the delayed matter outflows from the complicated merger. And as we heard, we have had, and I'm going to be zooming into this game-changing first binary neutron star merger that was observed in both gravitational waves as well as in every part of the electromagnetic spectrum, allowing us to pinpoint for the first time where a gravitational wave merger happened in the sky. This remains our only multi-messenger compact object merger we've discovered, and allowed for a whole host of discoveries that I'll touch upon in this talk. And so these gravitational wave mergers are really impacting several diverse fields in astronomy and physics, thanks to the tremendous advances in gravitational wave detectors, time domain astronomy, as well as big data and computational astrophysics. And so in the next 15, 20 minutes or so, what I'd like to talk about is what we have learned, as well as open questions from the field given current gravitational wave observations, as well as end up with perspectives and future, and include a discussion about future ground-based gravitational wave detectors. So just to make sure that we're on the same page, gravitational waves, they're an intrinsic prediction of general relativity. They're the perturbations in space-time curvature which are sourced by these time-varying quadrupole moments of the mass-energy distribution. Our measurable in gravitational wave astronomy is this dimensionless, time-dependent gravitational wave strain, which has this 1 over distance to the source dependence, allowing us to use these as standard sirens, as we heard in the previous talk. They have two polarizations, H plus, H cross. These act as transverse tidal waves, and indeed this is how kilometer, Michelson, and Fabry-Perot interferometers, such as the LIGO detectors as well as the Virgo interferometer, are measuring gravitational waves. They're essentially measuring a linear combination of the two polarizations weighted by the quadrupolar antenna function. And a worldwide network is absolutely critical for talking about following up these events with other facilities as well as telescope in terms of sky localization. So what do we want to learn from gravitational waves? So in order to detect as well as measure gravitational waves, we need to have these very accurate models of what the gravitational wave strain will look like. We call these gravitational waveforms, and they really describe the evolution of the final phase of these compact object mergers. They broadly comprise the so-called in-spiral, the merger, as well as the post-merger or ring down. And with these waveforms in hand, we can then actually cross-correlate our data stream with template banks of about 10 to the 5, 10 to the 6 of these waveforms and extract the following parameters. The redshifted masses, the spins, the tidal deformability, these are appearing in the phase, as well as geometric properties such as the inclination angle, the source position on the sky, as well as the luminosity distance, which appear mainly in the amplitude, and strong degeneracies exist. Now, there are two things I'd like to point out. Number one, the frequency of our detectors are sensitive to a particular part of the waveform depending on the masses of the progenitor. And this can impact how well we actually infer the parameters. The second thing I'd like to point out is that typically the analysis to do parameter inference, we use MCMC or nested sampling techniques, and they can take hours to days to weeks time scale depending on the complexity of the waveform that we're using. And this impacts gravitational wave or multi-messenger astronomy in terms of the follow-up. Now, one task to the community is to make sure that we input more physics as well as environmental effects into our waveforms. I'm showing a generic spin processing binary black hole merger waveform. And the second thing is to ensure that we can actually do faster analysis, resulting in precise and accurate measurements, and in this case we are leveraging machine learning techniques to really speed up the analysis by several orders of magnitude. Now, what have we learned? Well, number one, we've learned that compact object mergers exist and they merge within a Hubble time in our universe. The second is the rate of the binary black hole merger appears to evolve. The third is that there appears to be structure in the mass distribution of our compact objects with peaks at 10 as well as 35 solar masses at a few sigma. So, fourthly, we are able to say, or there seems to be indications that the magnitude of the spin component perpendicular to the orbital plane appears to be small, but indeed, actually, the spins are currently measured quite poorly. Another thing we're able to do is put bounds on the fraction or limits of the total energy density of the universe. This is from the first 3 science runs that I'm quoting here. And now when I come to GW 170817, I'd like to just spend a few moments thinking about the follow-up of this event. And so gravitational wave detectors themselves have very poor angular resolution. They're quadrupolar, all-sky detectors, and we essentially rely on using the triangulation of the arrival times of the signals to actually reconstruct the source. And so in the case of GW170817, we were able to localize the source to 30 square degrees with a distance of 40 plus or minus 10 megaparsecs. With this gravitational wave volume, we could then cross-match this with galaxy catalogs, and indeed, after 11 hours after the event, we were able to actually identify a bright blue flash in the galaxy NGC 4993 that really instigated this unprecedented global ground and space-based effort with over 100 instruments. And indeed, this multi-messenger discovery paper is where I spent most of my first few months of this event. Now, shown on the right here is a plot I really like, which sort of illustrates the panchromatic beauty of the observations in the UV, OIR, as well as X-ray and radio bands over a 3-year period. And what I'd like to stress here, firstly, number one, we were very fortunate because this was our strongest gravitational wave merge. It was so close by that that bright blue flash actually was our neutron star binary. We're not finding this in the case of our other gravitational wave neutron star, neutron star, neutron star black hole mergers, and indeed this is a big challenge. And the second thing I'd like to highlight is what made this observation so beautiful was that it broadly agreed with the prediction that there should be 2 types of matter outflows that are responsible for the 2 electromagnetic counterparts that we saw. So firstly, the kilonova, this rapid neutron capture nucleosynthesis powered transient thermally emitting in the ultraviolet, infrared, and optic UV, and resulted in the discovery of one of our astrophysical sites of heavy elements, as exemplified by the movie from the Very Large Telescope in Chile. And the second electromagnetic counterpart was we were able to actually confirm for the first time that binary neutron star mergers were the progenitors of short gamma ray bursts, allowing for insights into the nature of their relativistic jet. I'm highlighting one result here, which I'll return to, which was the VLBI constraints that allowed us to actually constrain the inclination angle of this binary a year after, so using radio observations from very long baseline interferometry. And so a few results just to highlight. The gravitational wave chirp you can hear. As well as the gamma ray burst that was heard 1.7 seconds later allowed us to actually constrain the speed of light with gravity to 1 part in 10 to the 15. The second is that we can actually use these neutron star mergers to probe the QCD phase diagram, and indeed may allow us to actually map the transition between hadronic as well as quark gluon plasma. Here I'm showing the first multi-messenger constraints of our gravitational wave binary neutron star mergers in the neutron star mass radius plot, the 50 and 90% confidence intervals being shown here, as well as using 2 rotationally powered millisecond pulses from the NICER telescope. And so this is where the field is going. You can see that we are preferencing more stiffer equations of state and already ruling out some more exotic equations of state. And we need about 50 strong of sources. In the case of the Hubble constant, we already heard that we were able to have our first bright standard siren measurement shown in orange. For H naught, what I'm showing in blue is the improvement of actually having this radio observation of the inclination angle breaking the distance inclination angle degeneracy in the gravitational wave side, which resulted in a factor of 2 improvement. And when we talk about actually resolving potentially the Hubble tension with this new independent method of measuring H naught, our simulations are showing that we need about on the order of 50 bright standard sirens to reach the 2% precision to discriminate between the low and high redshift measurements. Then So what would we like to learn? Well, for neutron stars, the nature of the remnant, as well as the neutron star equation of state. For black holes, we'd like to understand things about the formation channels. Why are the black hole spins so close to zero? And I'll just end now with the perspectives for future gravitational wave detectors. So we already heard, before talking about the gravitational wave detectors, I'd like to remind you that we are really now in this new era where there are new facilities, both in the optical as well as upcoming facilities in the radio, which are allowing us this really multicolored movie of the dynamic universe. And in addition, we also have these new facilities on the astroparticle side, also complementing this piecing together the jigsaw puzzle of the physics driving these mergers. Now, coming to the gravitational wave detectors, we have now moved in this era from individual objects to statistics. So what I'm showing here is a timeline of our global network, where the red line here denotes where we are today in our fourth science run. The numbers show the sky averaged orientation average distance that we can see for binary neutron star mergers. And we are already working towards developing the upgrades that will happen in the 2030s, the projects LIGO A-sharp and Virgo Next, for our pre-existing detectors, where we anticipate a hopeful factor of 2 increase in sensitivity, so that's a factor of 8 or so in volume. And of course, the construction of these new next-generation observatories, the Einstein Telescope and Cosmic Explorer. So what I'm showing here are the different designs, sensitivity curves for our current gravitational wave detector, the one and projected sensitivity for the late 20s, this A-sharp projected sensitivity, and that we anticipate and hope to have this 10 times improved sensitivity in the broadband, as well as shifting the seismic wall to the lower frequency with these next generation detectors, the Einstein Telescope and Cosmic Explorer. And what I'd like to stress is it's really this width and this depth of this frequency bucket that makes these observatories exceptional. Number one, allowing us to really have precise measurements for the very high signal-to-noise ratio events, as well as actually being able to be sensitive to parts of the waveform that we're not currently able to. So for instance, the post-merger remnant for neutron star binaries, as well as the detection potentially of intermediate mass black holes, as well as increasing the sheer volume, as well as rate of compact object binaries that we're talking about. So these observatories really are precise, wide, and deep. And so a brief description of the Einstein Telescope. The original plan is that it was a single observatory located 200 meters underground to beat the seismic noise, comprising 3 nested interferometers with 3 10-kilometer long tunnels, with this 10 times improvement in sensitivity. That's a factor of 10 cubed in terms of volume and rate, and being a facility that could last 50 years or so. In the US, there is the partner project, the Cosmic Explorer, which comprises a 40 and 20 kilometer L-shaped detector, similarly with a 10 times sensitivity, and the plan is to operate as a global network with the Einstein Telescope. And what I'd like to stress here is the sheer cosmic reach that these next generation detectors can go to. So shown here is the redshift as a function of total binary mass, with different signal-to-noise ratios denoted. And so, number one, these next-generation detectors will be able to actually push the cosmic horizon and the boundary to all the observable neutron star mergers, neutron star black hole mergers in red, binary black hole mergers in white, and actually observe most of the population. Secondly, we'll be able to observe actually new populations of black holes, those coming from population 3, the first stars, as well as the more speculative primordial black holes. And the third thing I'd like to stress, as you can see on this plot, the GW170817, as well as our first binary black hole merger, as well as our heaviest event, really being a signal-to-noise ratio of 1,000. So in the case of GW 170817, we're talking about measurements of a signal-to-noise ratio of 1,700 compared to the 32 that we detected in 2017, and individual mass errors of 10 to the minus 3% compared to the tens of percent that we were able to measure in 2017. Coming to the science case, I'm just listing for completeness really the treasure trove of the science case for these next generation detectors spanning both astrophysics and fundamental physics and cosmology, as well as the detection of new astrophysical sources, as well as potentially the stochastic background of the cosmological origin, as well as the nature of compact objects. And we can map these also to the science case for Cosmic Explorer. And there are just a few things I'd like to highlight at the end of my talk about these next generation detectors, which I think are just tremendous opportunities. Number one is the cosmic reach. So shown on this infograph from JWST, one of the most exciting discoveries has been the high redshift candidates for galaxies. And we can overplot where current gravitational wave detectors can see, and where detectors such as the Einstein telescope can actually go to. So far beyond the reach of current optical telescopes, and far beyond the reach of where we expect the first stars, as well as the furthest galaxies to exist. The second thing I'd like to stress is the sheer number of events because of this increase in volume. And so for a network with these two Cosmic Explorer and Einstein telescope detectors, we can anticipate hundreds of thousands of these mergers per year. Okay, the third is actually the necessity of having at least two of these next generation detectors operating. This is indicated in this polar histogram. I don't have time to go through it, but this is what you're seeing here are the different science cases as a function of different detector networks. And the reason we need to have two is not only for sky localization, but also to have additional polarization content to be able to actually measure things like the distance, inclination, and hence also break things like the redshift mass degeneracy that exists in gravitational waves. So if we want to talk about the high redshift universe, as well as also some testing gravity theories where polarization content is important, we really need to look at having at least two of these detectors operating. So just finishing, and I know I'm the final talk of the day, and so I hope in the conference dinner just that you will be thinking maybe at the back of your mind about the transformational era that we are witnessing at the moment in gravitational waves. Potentially, by the end of the 2030s, early 2040s, we are looking to actually detect not just the couple of hundred compact object mergers that we have seen in the last 10 years or so, but 10,000 to 100,000 of these mergers per year in gravitational waves. So what I'm showing in this donut plot is the look-back time in the radial coordinate. The yellow stars denote the binary neutron star mergers that are detectable per day. The binary black hole mergers in white per week, and the binary supermassive black holes that we may be able to see with LISA. I have not discussed the ESA-led LISA mission per decade. Okay, and you can see the horizon distance for things like the Einstein telescope in green, as well as Cosmic Explorer, and compare this to how far we will be able to go out in the 2030s. And so this means that for Multimessenger, we're not only talking about following up the very loud gravitational wave events to do either detailed nucleosynthesis, as well as to do other strong field astrophysics tests, but also cross-correlating. And we had a question about this already, the gravitational wave as well as electromagnetic source catalogs important for using these systems as large-scale structure and extragalactic astronomy. And so I've just focused on the high-frequency end of the gravitational wave spectrum. Many of the sources in the millihertz regime with LISA will also be gravitational wave mergers with electromagnetic counterparts. And so the future is both loud and bright. And with that, I'll just end with my conclusions. Thank you.
Thank you, Samaya, for the talk. Questions? There is one here in front. Go ahead. And then please go ahead.
Okay. First of all, very nice talk. Was amazing. Maybe I just have one curiosity in slide 20. In slide 20.
Slide 20, yes.
It's not my first time with this plot, and I would like to, if you happen to know, do you know why Cosmic Explorer, when they show this plot, they do not show the violet modes, while Einstein Telescope does?
No, I don't know per se. Sorry, I can't answer that question. But yeah, you can of course see it with the Einstein Telescope, but yeah, I'm not sure. I think just to give an idea of what the projected sensitivity is.
Hi, thanks for the talk right here in the front. So as you go to have, toward these hundreds and then thousands and hundreds of thousands of sources, it makes me as a particle physicist think of pileup, because now I'm imagining lots of these kind of little sine waves on top of each other. Can you give me an idea on how you separate those and actually resolve all of them? Have you done simulations to try to see how many you can disentangle with your sensitivity?
So we have actually started, we've embarked into trying to look at the data analysis challenges for the Einstein Telescope and Cosmic Explorer, because you're right, there will be tens, if not hundreds of signals that will be overlapping and that will be strong enough that we can actually infer parameters for them. And so there are several groups now that have actually looked into implementing machine learning simulation-based inference to actually address this challenge. But one thing I should stress is that in the case of LISA, we have a very similar issue in terms of a global fit problem, in terms of the diversity of sources, because shown here is the spectral density for LISA, but what you can see here in the blue, as well as the red ones, are known white dwarf binaries that we actually have already know about, but each one of these dots are actually monochromatic white dwarf binaries, where we're seeing, tens of thousands, which are actually resolvable above a coherent foreground of unresolvable white dwarf binaries. So indeed, over the last 20 years or so, there have been a lot of data analysis techniques developed in the LISA case, which I think will have a lot of complementarity in how we're going to actually make sure that we can pull out the strong sources as well as actually characterize the foreground from the unresolvable sources that we will see with Cosmic Explorer and Einstein Telescope.
Thanks.
There's been a question there. Samaya, to the right.
Yes, sorry.
Hi, thanks very much for your overview. I was curious because I saw in one of your slides, I think it was slide 23, you have a statement that the Einstein Telescope can probe the QCD structure. Can you expand a little bit on that? Because I'm wondering how you can take your gravitational wave signals and make inferences on the QCD constituents. I'm particularly curious about potential contributions from second-generation quarks, so strange enhancement, maybe even charm. Is that something within reach?
Yes, so if you look at the QCD phase diagram here, in terms of the high-density, low-temperature regime, this is where, at least the gravitational wave as well as the slightly hotter electromagnetic counterparts will actually probe. Yes, and so it really is through measuring essentially the so-called tidal deformability parameter in the gravitational wave phase, which allows us to actually say something about the nature of cold dense matter within the neutron star. And that is what we are hoping to, already with GW 170817, we could have constraints or upper limits, but this is where we actually hope to go with the future gravitational wave detectors. Now, at the moment, what we are limited by, with measurements like the tidal deformability, is that we are not actually seeing basically the merger or the post-merger of our neutron star, neutron star, neutron star black hole merger. It goes out of frequency band. But with the next generation detectors, we will be able to actually really have much more precise measurements and potentially signal-to-noise ratios of over 100 for binary neutron star mergers, putting 100-meter precision constraints on individual neutron star binaries. And so then it becomes very interesting on the mass radius plot for neutron stars to actually then say something about the equation of state.
Okay, thanks very much.
There is a question in the center.
Hi, this is a question related to what Ben asked about the pileup here in the middle.
Oh, sorry, hi.
Hi. So on slide 9, you show the energy density. I was wondering, is this like the totality of, on slide 9?
Yeah. So this is what we were able to constrain. So this is the totality of the contribution that we expect from the stochastic foreground from binary black hole, binary neutron star black hole merger, given the uncertainties currently that we can actually, the empirical measurements that we can make on the merger rates for these different populations. And this is the cumulative number that we were able to put in 2021 with the third science run. But this can be improved. And indeed, what we hope to do, I have a backup slide, sorry. In terms of the energy density, sorry, I apologize, is here. Yes, so this is essentially the limits with Einstein telescope as well as Cosmic Explorer that we can actually probe in terms of the energy density, the fraction coming from gravitational waves. So several orders of magnitude to what we are able to currently do. And of course, standard models of inflation, it's much, much lower, but of course things like cosmic strings as well as hybrid models of inflation as well as preheating may actually have signatures that will be detectable with these next generation detectors.
Okay, thank you very much.
Okay. We are going to have only one more question, so unfortunately he was before, so.
Okay, so the two related questions. So using standard siren, how well can you determine H0 in the future to resolve this tension, and also the whole expansion history, which will require network of optical telescopes into hybrid redshift?
Thank you for that question. I think I do have a plot, I hope, that can answer this, but if not, I will. So actually with, maybe it's not here, sorry, with current detectors, we estimate about on the order of 50 gravitational wave plus some redshift measurement either from the optical or the radio of the host galaxy. But those signal-to-noise ratios we're talking about being at threshold, they're typically signal-to-noise ratio of 10. We have this stronger signal of 30, and so we're talking about 50 of those binaries. Now, in the case of dark standard sirens, where this was the original idea proposed by Bernard Schutz, was that we use gravitational wave volumes and then cross-match them with galaxy catalogs. And so you can associate a probability with each galaxy in terms of it being the host of the compact object merger. There we need to have hundreds of these events to reach the 2% precision. Now, in the era of the next generation gravitational wave detectors, already within a, let me see if I can get this plot. Already within a few days, we can reach the several percent measurement. And so sorry, here you can see the numbers, but over a year we are talking about going to the sub-percent measurement in terms of the bright standard siren measurement. Yes, now that has a lot of caveats. For instance, I have not discussed systematic errors that may actually start to impact, such as gravitational wave calibration, but that is sort of the forecasting that current studies are showing, is that we can really probe, push down, and not only measure H0, but then also other cosmological parameters such as W, etc., to a great precision, yes, a quite mind-blowing precision, yes. I hesitate to promise this because I think, of course, in reality it's much harder, but this is the way we can go. In terms of making sure we have the counterparts, now that's another question. In terms of host galaxy redshift, which is what we really need, we can actually go out to, with the next generation radio or optical facilities like the Rubin Observatory, out to a redshift of 1. So there'll be some fraction that we will be able to follow up, and that should, if we have at least 2 detectors, much well localized. I mean, at the moment, some of the events that we have had, we've seen only with 1 detector, we're talking about 20,000 square degrees, or half the sky, yes? Here we're talking about, in the era of the late 2030s, potentially going down to a square degree for tens of these events, yes? And so then follow-up does become possible, especially for the golden nearby binaries. But we will also be able to exploit this more dark statistical method of just cross-correlating.
Okay, thank you.
Okay. So, I'm sorry, but we cannot take more questions because not only that we're running late, but I heard that we have to catch a flight, right? So let's thank Samaya again and all the speakers of the session.